When multiple processes compete for limited hardware resources, an operating system must manage every allocation with precision. This is deadlock avoidance, a proactive mechanism designed to distribute resources so that the system never enters a frozen or dangerous state. The foundational method for achieving this is the banker's algorithm, a technique developed by Edsger Dijkstra to determine if a specific request can be granted without compromising system stability. The algorithm is modeled on the way a bank evaluates loan requests. A bank never distributes its entire cash reserve at once. It first checks if it can still satisfy all its other customers' future needs. If a loan risks the bank's solvency, the request is delayed. The operating system uses the same logic. It treats hardware resources like capital, checking if it can fulfill the future needs of every running process before approving a current request. Ultimately, the algorithm is a risk assessment tool. If the allocation keeps the system mathematically safe, the resources are granted. If not, the request is postponed to prevent a total system failure. To maintain control, the operating system must constantly evaluate its state, a snapshot of which resources are held by which processes. Every possible condition of the system falls into one of three zones: safe, unsafe, or deadlock. In this diagram, a safe state is a condition with mathematical certainty that every process can finish. Unsafe describes a state where the system can no longer guarantee completion. Deadlock is a specific failure point nested within that unsafe zone, or processes are permanently stuck. The goal of the banker's algorithm is to act as a barrier. It prevents the system from ever crossing the boundary out of the safe space, ensuring that a deadlock never has the opportunity to form. To enforce these boundaries, the operating system maintains a dashboard of specific integer values for every process and resource in the system. The system tracks 4 metrics: available, maximum need, allocation, and need. Available is the master pool of free resources. Maximum need is the predefined limit a process requires. Allocation tracks resources currently checked out by a process. Without tracking these integers for every process, the operating system cannot project future demands or calculate the risks of a new allocation. To find a process's current need, the system subtracts its current allocation from its maximum need. If a process has a max of 8 and an allocation of 3, its need is 5. This integer tells the system exactly how many more resources the process requires to finish its work and release its held assets. When a process requests a resource, the operating system doesn't immediately commit hardware. It first performs a simulation. In a sandbox environment, the system temporarily updates the available, allocation, and need values to simulate the state if the request were granted. This is the algorithm's core, testing mathematical consequences in a virtual environment before applying decisions to the actual hardware. With 3 available resources, P1 needs 2 and P2 needs 3. P1 passes the check and receives resources. P1 finishes, returning its assets to the pool. The expanded pool now fulfills P2. This successful order is a safe sequence. This sequence proves the system is currently in a safe state. The simulation is closed and the original resource request can be approved. If we reset the simulation with only 1 resource available, the math changes. Process 1 needs 2 and Process 2 needs 3. Process 1's need is greater than 1, so it fails. Process 2 fails as well. The simulation stops here. Neither process can acquire enough resources to finish and release their held assets. Since no safe sequence exists, the OS knows that granting the request would move the system into an unsafe state. The request is rejected, and the system state is rolled back to its last known safe point. It is important to distinguish between risk and failure. Rejecting a request doesn't mean a deadlock has already happened. It means the system is crossing the boundary into an unsafe state. While every deadlock is an unsafe state isn't necessarily a deadlock. In this zone, processes might still finish if they don't actually request their full maximum need. However, the operating system can no longer mathematically guarantee that outcome. Deadlock is a state of certain failure. An unsafe state is a space of unmanaged risk, where the OS has lost its guarantee of completion. In modern software engineering, the banker's algorithm is rarely implemented purely on general-purpose systems. The algorithm's biggest hurdle is that it requires every process to declare its maximum need in advance. In modern systems, resource demands fluctuate dynamically during execution, making those advanced declarations nearly impossible. Because these demands change unpredictably, a system cannot always rely on a static max value to perform its safety checks. Additionally, when a system is running thousands of processes, the computational cost of constantly searching for safe sequences creates significant overhead. Most modern kernels favor simpler detection or prevention methods over the banker's algorithm safety checks. However, Dijkstra's work established the definitions of safe and unsafe states that remain the standard framework for analyzing resource stability. The banker's algorithm remains a cornerstone of computer science because it introduced a vital design philosophy, using proactive mathematical modeling to completely eliminate the possibility of a system failure before it can ever begin.